Welcome to For the Love of Physics, a special welcome to all the students at Ishik Boys High School, especially those in Mr. Jager's classes. Today we're diving into something that sounds big, maybe even a bit intimidating, foundational questions of physics. But here's the thing, our mission today is to show you how physics is already like a huge part of your everyday life, stuff you do without even thinking. And then we'll explore the really methodical way scientists actually figure all this stuff out. The source material we're using, it's actually from a physics textbook, so it connects right back to what you're learning. Okay, let's unpack this then. Seriously, you probably know way more physics than you think, even if you haven't, memorized formulas yet. Think about this. You buy ice cream, right? First thing you do at home, stick straight in the freezer.
Right. Obvious.
Well, yeah, but why? You're not just being neat. You're using physics. You just know heat makes it melt. That basic understanding. That's physics right there.
And what's so cool about that is how these really basic ideas link up to, well, everything.
Yeah.
And how we figured them out. This isn't just about learning definitions. It's more a journey into like how physicists actually think, how they look at the world.
Totally. And the ice cream is just one tiny example. Every single time you, take a step, or catch a ball, open a door, even just glance in a mirror, you're kind of relying on physics without realizing it.
It's baked into how you move, how you interact with things.
Exactly. It's not just theory in a book, it's lived. Like how you know how hard to throw a ball or how to brace yourself to catch one.
And, stepping back a bit, that's why physicists started organizing all this knowledge. They put things into categories, these big areas of physics, not to make it harder, actually, but to make it easier to handle, to break down really complicated problems.
Yeah, makes sense. Like organize the toolbox.
Precisely. It helps you figure out which tool or which principle you need for a specific problem.
And you can see this super clearly in something like a car. Our source uses that example, and it's great. Building a car, running a car, it takes so many different types of physics working together.
It's like an orchestra, really.
It is. Every time you start it up, it's like, bam, physics symphony. Okay, so, for example, thermodynamics.
Heat and energy.
Right. That's crucial for making engines efficient and, for the coolant stuff that stops them melting.
And then there's electromagnetism. Can't forget that.
No way. The battery, the starter motor, the headlights, all that relies on controlling electricity.
That spark of life for the car, literally.
Optics. That's about light. So, headlights again, obviously, so you can see where you're going.
And mirrors, seeing behind you.
Yep. And making the ride smooth. That involves vibrations and mechanical waves. Think shock absorbers.
Oh yeah, it makes a huge difference. And radio speakers too, right? Sound waves.
Exactly. Even sound insulation, keeping things quiet inside. That's waves.
And the most basic, maybe, mechanics.
Definitely. The wheels spinning, the tires gripping the road, that crucial friction for traction, that's all mechanics. Motion, forces.
Without mechanics, it just wouldn't move. Simple as that.
And it's not just complex machines like cars. Think about sailboats. Totally different thing, but same deal.
Okay. How so?
Well, sailboat designers need to get the physics of fluids right for the whole shape, so it floats properly, stays stable, but is also easy to steer.
Right, how it moves through water.
And they need the science of motion and its causes, forces, basically to design the sails, get the shape and arrangement just right to catch the wind efficiently.
Makes sense. Using the wind's force.
Then building the boat itself, balancing all the weight and stresses, that's pure mechanics again. Every single piece is physics.
It makes you wonder, where did this word physics even come from? How did it all start?
Good question. The source mentions its roots, Latin, physica, Greek, physica. Both basically meaning natural things.
Natural things, okay.
Yeah. And early thinkers, like Aristotle, saw physics as, studying nature. But interestingly, he thought math wasn't really part of mechanics.
Huh. Really? That seems odd now.
Right. Because then came Galileo, and he really disagreed on that point.
Galileo. Big name.
Huge. He was key in changing mechanics because he insisted on using mathematics to describe motion. He didn't just observe, he measured, quantified things.
So he shifted from just philosophy to actual science with numbers.
Exactly. He changed how we ask questions, made it about experiments and measurement, not just debating ideas. So, okay, we notice physics everywhere. Cars, sailboats, ice cream. But how do we go from just noticing to actually understanding it? systematically, provably.
Yeah, how do we know it's really true?
Well, that's where it gets really cool. It's this process called the scientific method. The book calls it a systematic method of studying natural phenomena.
It's like the official rulebook for discovery?
Pretty much like a detective's toolkit for the universe. Step by step. Rigorous. It's the engine driving science.
And, well, sometimes discoveries happen by, luck.
A happy accident.
Yeah. But real, steady progress, that relies on this careful process. Observing, gathering data, making educated guesses, hypotheses, testing them, and then building theories. It's logical.
Okay, let's break that down. First step, observing and asking questions. This is basically using your senses, right? To gather info.
Qualitative, like what color is it? Or quantitative, like how long is it? Numbers.
And physicists get specific. They focus on what they call a system.
Right, the little piece of the world you're actually studying.
Yeah, you zoom in. Like if you're studying a ball flying through the air, the system is the ball and its motion. You ignore, I don't know, the color of the ball or the brand logo.
You filter out the noise, basically. Focus on what matters for your question. That's a skill in itself.
Totally. And once you have your system, you often simplify it even more with a model.
Ah, like a sketch or a diagram.
Kind of. It's a simplified version showing just the key things affecting what you're studying. Like for that basketball's flight, you might just draw its path, the arc, not the whole court or the player.
Got it. Strip it down to essentials.
And what's fascinating, observation isn't always just looking at things.
Oh, like what?
Well, think about Galileo again. He did thought experiments. He imagined stuff.
Right. This famous one about dropping things.
Exactly. He imagined dropping two identical objects from the same height at the same time, and just by thinking it through, he figured they'd land together. Same speed.
Which went against what everyone thought back then, didn't it? The whole heavier falls faster idea.
Totally against it. It's amazing he could see it just using logic.
Yeah.
So yeah, the old idea felt intuitive, heavier should fall faster. What was Galileo's thinking there? How did he poke holes in it?
Well, his genius was showing the contradiction. If heavy falls faster and light falls slower. What happens if you tie them together? Does the slow one slow down the fast one so they fall somewhere in between? Or does tying them make one heavier object?
Ah. And if it's heavier, according to the old idea,
it should fall even faster. It couldn't be both. That paradox showed the old idea had to be wrong. He used a mental model to break it down.
Brilliant. Okay, so you observe, maybe even just in your head, and that naturally leads to asking why. Which brings us to step 2, building hypotheses.
The educated guess?
Right. The source calls it a logical and acceptable interpretation of reality as observed or thought. Basically, your proposed explanation, something you can test.
So, back to Galileo. He was trying to figure out what factors, mass, shape, air resistance, affected falling speed.
And his thought experiment about tying the objects led him away from the common belief.
Which would say tying them makes them fall faster.
Right. But Galileo hypothesized the opposite. His hypothesis was super clear. All objects fall at the same rate in the absence of air, no matter what size they are. Bold move.
Very. Especially then.
Which leads right into step 3. Testing hypotheses, analyzing data, and deducing results. This is where you actually do something. You run experiments.
Gotta check if your guess holds up.
Yeah. And if the experiments show your hypothesis is, well, wrong,
then you have to change it. Or toss it out completely and start over. Science is tough sometimes.
True. Now, for Galileo, testing this was tricky.
Yeah, big time. His tools weren't great, right? Hard to time, these falling fast.
Exactly. And he couldn't just, switch off air resistance, no vacuum chambers back then.
So how did he test it?
Ingenious solution. He couldn't slow down falling, so he used balls rolling down smooth ramps instead, like a slow motion version of falling.
Ah, clever. A model again.
Yep. The steeper the ramp, the closer it was to actual falling. He could actually measure that, collect data, and the data supported his hypothesis.
Even without perfect conditions. That's smart experimenting.
It was a great example of a controlled experiment. He'd change just one thing, like the ramp's angle, and see what happened. Keep everything else the same.
Critical for knowing what's actually causing the effect.
Okay, so experiments are done, data analyzed. What's next? Step 4. Communication and establishing a theory.
Sharing your work.
Right. If experiments keep confirming your hypothesis, again and again, then scientists try to build a theory.
Which is like a bigger, more general explanation.
Exactly. It explains why things happen and can even predict new things you haven't tested yet. That's the power of a good theory.
But what if the tests don't work out? You mentioned revising the hypothesis.
Yeah, absolutely. If the results don't match, first you double-check your experiment, repeat it, make sure you didn't mess up.
Fair enough.
But if it consistently fails, the hypothesis has to be revised or abandoned. And crucially, you publish your results, success or failure.
So other scientists can check it?
Precisely. Science is collaborative. Other people need to be able to replicate your experiments and get the same results for a theory to really be accepted. It's a self-correcting system.
Keeps everyone honest, basically.
So wrapping this up for today, we've seen physics isn't some abstract thing just for labs. It's in your car, it's in sports, it's even in your freezer with the ice cream.
It's truly everywhere.
And figuring it all out isn't magic. It's this careful, logical process, the scientific method. Observing, hypothesizing, testing, sharing.
And the key takeaway really is that you're already doing physics intuitively. And you can absolutely think like a physicist. That scientific method, it's not just for science labs. It's a powerful way to approach any problem, really. Look carefully, make a smart guess, test it out, see if you're right. You can use it in everyday life.
That's a great point. So here's something for you, our listener, to think about. Pick an everyday common sense idea you've always just accepted.
Like maybe wet roads are always more slippery than dry roads, or something simple like that.
Yeah, or how a certain type of ball bounces, or maybe something about cooking. Now, thinking out the scientific method steps, observing, hypothesis testing, how could you design a little experiment, even just a thought experiment like Galileo, to really check if that common sense idea holds true?
Stay in contact with your physics teacher. Stay creative.